Guys, we were talking about Suzuki reactions in the last video, and I showed you how easy these things need to be because they do not need to be any more complicated than just gluing them together. That's all that we need to do. So let's take a look at another example. Here we're going to have a ring. There's my benzene ring. And off of this, let's put a methyl group, a CH3, just to make it spicy. You like it spicy? All right. And then here we'll do a bromo group. And we're going to react this with a boron-containing group. And that boron is a CH double bond. Let's do a CH, CH3. And then here, on the other side of the boron, let's do O and O. And bring it back around and draw this benzene ring and be fancy and pretend like we're smart with organic. And we'll do PDL2 and NaOH. Phew, that's a lot, right? That's a lot of stuff. But it takes longer to write down the reagents and the catalyst than it does to splice these things together. Let me prove it to you. Here's our reagent. I'm going to redraw it. There's my ring structure. There's my CH3 group. Here's my bromo group. So I'm going to take my eraser. There it goes. And now I add on the piece that's connected to the boron. This is a CH double bond CH CH3. There you go, folks. That's all there is to it. No more. That's it. Once more, this halogen group is a aryl group because it's attached to a benzene ring. And this boron-containing group satisfies the need for Suzuki. This boron-containing group is attached to an sp2 carbon. So that is one of these alkynyl groups because we said that sp2 carbon is okay with the boron-containing group. All right, so now that we are a little bit more familiar with Suzuki, a couple of things I want to talk about when it concerns palladium. A lot of times in a general chemistry class, palladium and many of these other transitional type of metals get ignored, right? They get thrown on the back burner because they want you to learn things like silly ice charts that you'll never use ever again. All right, well, palladium is one of these groups of metals that we call PGMs. And PGMs stands for these platinum group metals. There is a group of metals that's around platinum, and they all behave a very similar way with us in a laboratory environment or when we do things with them. So palladium is one of these. And here is our PGMs. So palladium, platinum, rhodium, ruthenium, iridium, and osmium. So all of these metals, folks, it's not uncommon that they behave very similar that palladium does. And right now we're on the move. Right now we are on the move of trying to figure out more organometallic reactions with these metals, what they can do, what can't they do, can we trace the mechanisms down, do we really fully understand them to bring them into the world of organic, yes or no? So PGMs, again, very common group. Think of these like everything in the alkali group, everything in the alkaline earth group, everything in the halogen group. They all behave a very similar way. And PGMs are also part of that vat. So these PGMs, we do have uses for them, of course, right? I mean, they're on the periodic table. We have made things with them. We use them for different purposes. Everything from computers to catalytic converters in your cars and fuel cells. And because we're talking about palladium, one of the statistics that I'd like to give you is that almost 50% of the palladium sources come from Russia. So that is where we get our palladium. That's where the majority of the world gets their palladium. They have palladium vats, caves of it, if you want to think of it that way, that they can basically mine and distribute out to the countries that need to use it for whatever purpose that they need to use it for. All right, so a little bit about the mechanism, just a quick review. So some notes that are topped out, and it's not my chicken scratch. So first you need to understand palladium is inserted between the carbon and the halogen. So what we do know about the mechanism is that when we take this halogen group and I get rid of it, okay, well, we do that for a specific reason. The palladium is very much like copper or very much like magnesium. It kind of squeezes in between that carbon and that halogen, and it's this middle man now that kind of takes over, and this palladium is kind of holding hands with the carbon group and with the halogen group at the same time. We're also dealing with boron, right? I mean, we're talking about boron, and off of this boron, there typically is a carbon. It could be an sp2 carbon, an aryl carbon, just a normal carbon chain, but it's a carbon and a boron bond. So another thing that we need to mention is the electronegativity. Remember, I told you in the last video, where's boron on the periodic chart? And I told you to think about electronegativity when I did that. Well, carbon is more electronegative than boron. So just like before, what's happening here is that this carbon is becoming negative. And that is why this is getting added on to this particular carbon, because I want you to think of this almost like a positive carbon that begins to get formed. So here we have this negative and we have this positive that come together. So think of this as the nucleophile of the reaction. Again, we're not going to go into details, but it gets us another step closer of where our mind needs to be when this reaction goes forward. We're also talking about substitution in a way. So wherever this halogen is at, there it goes, and we get a new group that goes on in its place. That does not allow for rearrangement. So remember the mechanism I said was cyclic. The bonds break and the bonds form all at the same time. So what that means is that no rearrangement is going to happen in the molecule. So these are true SN2 reactions. That 2 should not be little. This should be a little n and a big 2. So these are SN2 reactions. It's a substitution, nucleophilic, and this bimolecular basically means second order almost in a way, right? It relates to kinetics back in Chem 251. So the palladium is eliminated, the halogen's eliminated, and this allows the new carbon-carbon bond to be formed. So here is the mechanism of the palladium Suzuki reaction. At least what we know of it. Do you want to memorize this? I don't think that you want to memorize this. Do you want me to ask a question about this mechanism on a test? No, you don't want that either. Look at this, folks. This is unlike any of the mechanisms that we've seen before, and this is the problem with organometallics. We have a general idea, again, of how the reaction goes forward and how it works and why it works, but we cannot deliver to you the exact concrete details of every step of how this product is formed. We do a pretty good job sometimes, but nothing set in stone. The way that you need to look at this mechanism, and again, you don't have to draw it, so you better not be writing this down. That would be silly. Step number 1, palladium. Look at the charge here, 0, formal charge of 0. Step number 2, we bring in R2X, which is our halide. Step number 3, we have the palladium squeeze in between the carbon and the halogen. Step number 4, it looks like we bring in some type of base. Right? Base. That's on the arrow. And that base is going to come in and pull the halogen off and replace it with a strong base. So almost like a substitution reaction that happens there. Then it looks like over on the other side at step number 5, we have this boron-containing group that has a halogen on, that has a alkyl group on it, some type of carbon. And that also is in the base, same base as what the palladium compound was in, because they're in the same flask. And number 5 goes to number 6 in a very similar way. The base comes onto the boron and creates this negatively charged boron. Well, when this piece for 6 and this piece for 4 come together and say, hey, hubba hubba, we get 7, which is a charged boron. We get 8, which is a palladium that has the two carbons connected together, and then we'll eventually get 9 when the palladium leaves. Also notice we start off with palladium at formal charge of 0. At the end of this process, it goes back to that, defining the proper definition of a catalyst. It can't get used up. It speeds the reaction up, but it cannot be used up. Also, take a look between step 1 and 3. The palladium has a formal charge of 0, then it goes to formal charge of 2. So we see a change of state. Well, here's the wording that they give us. You ready for this? The mechanism of the Suzuki reaction is best viewed from the perspective of the palladium catalyst. Oh, okay. So that's here. Okay. Not a big deal. The first step is the oxidative addition of palladium to the halide 2 to form the organopalladium species 3. Again, fancy terms, fancy words. What does that mean? It reacts with the halogen for 2 to give me the middleman palladium 3. Reaction with bases give intermediate 4. Okay, so a substitution reaction happens where the halogen gets substituted for the big bulky base that we bring into the picture, which via transmetallation with the boron 8 complex 6 forms the organopalladium species 8. Okay, so that's a fancy term or sentence that basically means this group that boron has is going to be slapped onto the palladium here in another substitution, basically, and we get this palladium with an R group on both ends. Reductive elimination of the desired product 9 restores the original palladium catalyst 1. Okay, I think you get my picture. They like to use a lot of fancy terms, a lot of fancy words in organic chemistry to make it more complicated than what it needs to be. Here's all of that boiled down into a couple of Tracy terms. Palladium comes in, reacts with the halogen to form a middleman. The halogen gets replaced by the base. That reacts with the boron group. Palladium is the matchmaker. That hooks up the R group to the left to the R group to the right. That new couple fall madly in love and go away, and the matchmaker takes the money and bam, starts all over again with a brand new person. And that's kind of what goes on here. We also need to talk about the preparation of the boron. We've really kind of left that over to the side. We've talked about these reactions, but, sometimes preparing the reagents are very important as well. We saw that with magnesium and lithium and the copper lithium, the Gilmans. We saw that every step along the way so far. Well, here's no different. We like to produce these boron-containing groups as we go. So, for instance, if I have some type of random group with a carbon double bond carbon at the end, then this is fair game for a boron that we have been using in these reactions. It's just one version. It doesn't have to be this. It's just one version. These two things react very easily together, and what you would see is this boron-containing group at this point, and this 5-membered ring. There's the 6-membered ring that comes along with it. What you would see is a substitution almost in a way. This boron that had a hydrogen to it is just simply going to be connected to this CH2 double bond CH. That's really all that it is, except the reaction kind of has to happen here. We got to clean this up. We can't have 2 hydrogens, 2 bonds to the left, and a bond to the boron. It's not going to work. So there is a reaction that takes place here. What happens is that the bond will break. So if you start off with a double bond, it goes to a single. If you start with a triple, it goes to a double. But that double bond will break, and you end up getting something like CH2, with a single bond that goes to a CH2. So this is the formation of the boron, and very often we have to do that in a lab as we prep this material. So this would be happening maybe in a different flask in a different part of the lab, and we would make this reagent, and then we would turn around and use this reagent inside of our reaction vessel. That way we can add the palladium to it and add our halogen to it as we need or as we see fit. Here's just another example of that. Down here at the very bottom, you're going to see the same kind of thing to go on. We can make these very easily. The only thing we do is bring in our borane. And this boron-containing group, it doesn't have to be this one. I mean, this can be like the ORs and the ORs with long carbon chains that come out here. It's perfectly fine, no big deal. But this triple bond attaches to the borane, and it breaks to a double bond. And that's what you're seeing here. There's our double bond, not a triple. Trans, as you would expect, is going to be the proper stereochemistry for those products. And the reason is because trans is always more stable. All right? Okay, so let's take a look at another example. So for part A, we have this molecule that has a halogen on it, and we are reacting this boron group that has that halogen or that alkyl group on it, and we're mixing in palladium and base. All right, so those are the ingredients for Suzuki. So let's do a Suzuki! All right. So let me clear the screen out. And here is our first component. And then we have our second component, our boron. And over here, I'm just going to put blah. Okay? I don't really care what else is over there. It doesn't matter. We're not going to do anything with it. So off of this boron is a carbon, double bond. Then that bond comes down. 1, 2, 3. And we want to know what happens when I put palladium in the mix. And I just want to say, every time I do Suzuki, you know, that is coming from an 80s child with a Super Nintendo and Street Fighter in front of me as one of the first fighting games that was kind of back in the day. So late 80s, early 90s, Street Fighter, you know, go back and take a look at some of those YouTube videos if you haven't been privy to that information. So, you know, what a wonderful time to grow up. So I'm going to take these two reagents, I'm going to mix them together with palladium into a Suzuki reaction. Okay, so here's how we do this. I'm going to start with my reagent. There's my bromo, and there's my double bond. And then I'm going to, there goes the bromine. And then off of this bromine, I need to connect this piece. And there's my bromo, or my boron. And that boron is connected to a carbon that is right there. It's an sp2 carbon. So folks, I need to keep this. So off of this comes a double bond, and that double bond has a bond that kind of points off of it, and then it looks like 1, 2, 3 more carbons. So 1, 2, 3 more carbons, and there you go. That's it. That's all you got to do. I mean, there's the Suzuki reaction of those two reagents coming together with palladium, and there's my product. It looks ugly. Granted, I know that. It does look ugly. But, folks, as long as you write the proper product with the proper number of carbons and hydrogens and so forth, I'm going to count it correct. I don't really care if you make it pretty or not. Just put what needs to go onto the sheet of paper and we'll call it a day. I mean, I can only ask so much, right? Organic can't require everything from us, or can it? All right, so let's take a look at B. All right, so for B, I got a dot, 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 dot with a double bond, and then off of this is a bromo group. And I'm going to react this with a double bond, and that goes to a boron with a big old blobby thing over here. All right, and PD. Okay, Suzuki! All right, so 1, 2, 3, 4, 5, and there's my double bond. So it looks like from up here, there is my bromo group. What do you think I'm going to do? There we go. It goes away. And off of this group now, there's my boron. That boron is connected to a carbon. All right, so that's that carbon. That's what that carbon's going to be. That carbon has a double bond, so I'm going to draw that double bond, and then off of that double bond, I've got 1, 2, 3 more carbons, right? So 1, 2, 3 more carbons, and there's my product. That's it. That's all that you have to do with Suzuki reactions. You don't need any more than this. You ready for another? Okay. Let's look at another example problem. By the way, all of those examples had Vinlic or aryl halides, and they also met the criteria for the boron, which meant an alkyl group, an alkenyl group, or an aryl group. So just to kind of reconfirm them, I know that we didn't check them as we went, but we just assumed that these reactions went forward. So we should be checking them, though. That's one of the things we got to look out for. All right, so let's look at another example. 1, 2, 3, double bond. That gives me a bromo group and a bond that goes right there. Plus, let's do this ring structure. Delocalized. Bring a boron off of it. And up here, I'm going to do OCH3 parentheses 2. Okay, well, this is the blah, blah material. Doesn't really matter. What's on the other side of the boron? I don't care. You shouldn't care. It doesn't matter in the reaction. Leave it alone. I see a boron. That boron is connected to a piece, and that piece is the only thing I need for this reaction. That's it. No more. Okay, so I need to react these two things together. Now, let's just double check. I just mentioned it. We didn't double check the last ones. Okay, well, let's double check these. Here is my bromo group. That bromo group is on a carbon. That carbon is sp2. Ding, ding. Okay, that meets that criteria. Here's my boron. That boron is directly connected to a carbon in a benzene ring or a delocalized ring. Ding, ding. That meets the criteria. Here's my palladium, and that palladium is there with an L2 probably. I just don't write it, but it's understood to be there. And there's also base here too, and I've not been writing it, but it's understood to be there. So don't let those throw you off. So my product, 1, 2, 3, there's my double bond, there's that one, here's my bromo group. I'll always start with a reagent. You know how I operate. And then I'm going to that bromine off. And that boron is connected to that ring, right? Okay, so that means that this carbon is going to be connected to something, and that is the carbon that's involved in that ring. And that is a 6-membered ring that comes through. So this is the structure of our product. Keep in mind, boron, there's that carbon. That's what it's attached to. So here, it's that carbon that replaces the halogen. Folks, nothing more complicated than that. No mechanisms, no curvy arrows. Makes you very, very happy. It makes me happy too, because I don't want to grade it either. All right, so let's look at another one. This is D, not B. We have a ... with an iodine and a double bond that's here. And then we're going to react this with, let's just keep another ring. And the boron has that. Same as before. I just drawn it a different way. Last time we just put it in parentheses and we said OCH3 2. And that 2 basically means 2 of those groups. And that's where 2 of those groups are going to be located. So we need to Suzuki. All right, so I have a halogen. The halogen is on an sp2. Ding, ding, it meets that criteria. I have a boron. That boron is on an aryl group. Ding, ding, it meets that criteria. Suzuki can happen. I'm just assuming base is there. So, what kind of product gets formed? Okay, here we go. I'm going to start with my reagent. There's the iodine, there's the double bond, there you go. And then what do you think I'm going to do? You make the noise this time. There we go. I think that sounds like turkey. All right, and then off of this structure, my boron is connected to a carbon, and that carbon is part of a larger ring. So here, there's where that carbon's going to go. That's where my halogen was. And this is part of a larger ring. And there we go. Nothing more than that, folks. We've just wrapped it up. Really, for Suzuki, that's really all there is to it. If you can do these types of things, then organometallics will not be a problem for you as far as the lecture material goes. All right, now let's take a look at another example. While we're on a roll, don't stop it yet. We're having fun. Here's two more examples. 3. What aryl or Vinlic halides would you use to synthesize the following compounds using the alkynyl organoboron compound shown here? All right, so now they're playing a little dirty because part A, this is a product. So they want to know, what would you mix with this thing to make this thing? We're working backward in a way. No more complicated than what we've been doing. Why? Let me show you. Look at this. This boron is attached to a carbon that's involved in a double bond. And this is a 1, 2, 3, 4, 5 membered chain. I was going to say ring, but it's not a ring, it's a chain. All right, well, look for part A. Look right here. There's my double bond. There's 1 carbon, 2 carbon, 3 carbon, 4 carbon, 5 carbon. Folks, this piece that's attached to the boron is right here. So what this means is that this piece was added on to a halide. So this was not there, and instead what was here was something like a halogen. And in the directions, it just says a halide. It doesn't really tell me which one, and I'm just going to put a bromine here. So that means that for part A, this was made by taking this ring with a bromo group on it. And we took the bromine off, and we replaced it with this carbon chain. Carbon, double bond, carbon, 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 carbon. There you go. That's all that there was. Now, I know where your head's going. You might be thinking, well, wait a minute. I thought that we did something to that double bond. No, we did not. We didn't do anything to these groups that were already attached to the boron. What you're thinking of, if that's where your mind went, you have to be very careful. That was the prep of the boron-containing group. So what this means is that if I wanted to make that boron to react this thing with, how would I do that? Well, I would take my boron group that had the hydrogen and then the stuff over here on the right-hand side, and I would have reacted that with a carbon triple bond carbon with the pieces that come out over to the left-hand side. So this triple bond would have broken, it would have ended up with a double bond, and this piece would have attached to the bromine. This would then react with this aryl halide in order to give me the product that's down here below. So you do nothing. We have not done anything to those carbons or that group that's attached to the boron. Once more, if that's where your mind went, like you think that you had to do something with that double bond, it was simply because we talked about preparing the boron reagent first. But that's not what this question said. All right, so now let's take a look at B. If we take a look at B, same kind of story. What kind of reagent should I be using to react with this thing to make that product? Once more, 1, 2, 3, 4, and then a double bond to the 5th carbon. All right, so 1, 2, 3, 4, double bond to the 5th carbon. So this is the piece that has been added on due to that boron group. So I'm going to cross this out. We do not need that. And instead, we need a halogen that's there. So here's my ring. There's that carbon, double bond. There's that bond that goes out. And this will end up needing a halogen. It didn't tell me which one, so I'm going to put an I there. Iodine works, just like bromine works. Not a big deal. Both of these are going to be perfectly okay. Once more, let's double check ourselves. This bromo group is on an aryl group, so ding ding, that works. And then this iodine is on an sp2 carbon, and ding ding, that works as well, because these halogens need to be Vinlic, or they need to be aryl. All right, now finally C. Let's take a look at that one. 5 carbons, and between 4 and 5 is my double bond. That's the piece I need to add on, so I do the same thing. 1, 2, 3, 4, and there's my 5th. So this is the piece that adds on. I'm going to circle it, and I'm going to cross it out, because this came from the boron. So what was here before? All right, well, what we used to react with, there is my ring. Off of this is a carbon with a double bond, and that eventually went off to the piece that we crossed out, which means that this is where my halogen has to be. Is that acceptable? Well, take a look at this. Bromine is on a carbon, and that carbon is sp2. So yes, this is perfectly okay for the Suzuki. All right, so there's a different type of question. It relates reactions and Suzuki and the requirements. Now, this next question is going to say, what hydrocarbon would you use to prepare the organoboron compound in problem number 14? All right, so just so I don't have to flip the slide, I'm going to draw it right here. So that boron-containing group that we just used looked like this. So this is where we're going to start. Here is my 5-membered ring, and off of this is my benzene ring with the delocalized system. And this boron went a carbon, double bond, carbon, and then we received 1, 2, 3 more off of that. So this is what they're referring to. And they say, what hydrocarbon would you use? Okay, let me show you how easy this kind of question is. You look at this boron group, and you look at what's attached to the boron. There it is. And you get rid of that bond. And then there had to be something there, right? And that's an extra bond that was there first. And folks, right there is the piece that was required to react with that boron group to make the reagent that we needed for the Suzuki. Again, that's all that these questions need to be. That's all that they should be. It's all about what was there before, how can we change it to make something new. Finally, one more, and then we're over for Suzuki. Here's another example problem. The steel reaction is similar to Suzuki, but it uses tin, an alkynyl organo-tin compound. And this is very similar to how Suzuki operates, but in Suzuki we often said trans is going to happen. Trans, that's the most stable. Well, the steel, kind of special because it gives me the cis form. So here down below we get this question, this reaction, and it says, okay, we didn't do a lecture on organotins, but you know what, folks? No difference. This is going to be okay. We'll take this ring, we'll add the bromo to it, and then here was a cis alkene that included tin, which is SN. And just like before, we see this palladium that's also used, L2, There we go. So not boron-based, it's tin-based. It does the same thing. It's still rooted as a palladium reaction. It's still rooted as a coupling reaction. There's no difference in how this process works. That's what the question basically told us. The issue is that this will keep the cis notation. All right, well, no big deal. What I'll do is I'll start with my ring. There's my bromo group. And again, make the noise. There we go. It goes away. And then here's the tin, and that tin is connected to a carbon. All right, so that's what this carbon's going to be. And this carbon has a double bond with it. There it is. And that carbon leads to another. But it keeps the cis notation, so I draw it down, not up, to make a trans. There we go, folks. That's all that this question wanted, really. I mean, if we take a look at this again, it replaces the alkynyl organoboron compound of the Suzuki with an alkynyl organo-tin compound. All right, so that's what we saw here. Unlike the alkynyl organoboron compound, Suzuki, that always has a trans configuration, well, this tin compound can have a cis configuration, and we saw that drawn. It's right there. There's the cis form. What is the product of the steel shown here? That's it. That's all that we had to do. It just gives us this idea that there's other options that are out there. If stereochemistry is a thing that we have to watch out for, then this is how we do it, folks. We've got different Batman assortment tool belts that we can pull into the gadget world of organic reactions and use. And this is another one of those. All right, so that's it with Suzuki. We're not done with palladium reactions, though. Remember, there's one more. And that other one is called the Heck reaction. Heck! I thought we were done. No, not yet. All right, so that's where this video is going to stop. In the next video, we'll pick up with the Heck reaction, and I can show you maybe how easy this one is, just like Suzuki. If you were comfortable with this, I think that you'll be comfortable with the Heck. All right, so until you hit play on the next one, I'll see you then.